Hey everyone, welcome to another session of CeerazzleDazzle Physics. In today's session we're going to be talking about direct and alternating current. So, direct current and alternating current. Right, mixing up my words here. Right, so we'll start off with this. Let's say we have a simple circuit. Right now we can see that the current will always flow from one direction, the positive terminal, all the way around here. Is it changed in direction? No, so it's always going in the same direction, all the way around. This is called direct current. So direct current, it flows in one direction only. So it never swaps direction. But we have something else. We have another diagram over here. Looks very similar, but instead of having a cell, I've got an alternating supply. So look, if we have direct current that flows in one direction only, we can kind of guess what alternating current is. Alternating current swaps direction as time goes on. So the current might go, so I'm going to use a different colour pen for this, for you guys to see. The current might go this way first. Yes, the current goes this way, and then after a while it will swap and go opposite way, then it will swap again and go opposite way. So the current is continuously swapping direction. It's kind of hard to draw on here, but just make sure you understand that the current goes one way, then swaps the other way, then swaps again, and swaps again. So alternating current, let's put that down, a formal definition. So put it on here, AC, alternating current. The current continuously changes direction. Bit awful spelling, but that'll be fine. So AC is constantly swapping direction, DC is always going to flow in the same direction. Right, how are we going to show this? Now, how on earth are we going to look at this in terms of physics? So we have devices in physics which are called oscilloscopes. Oscilloscopes let us look at electrical traces. They're basically like a piece of graph paper which hasn't got any scales on them. What you've got to know is that for every single oscilloscope there are two axes. First of all, one of them on the y-axis, this one is going to be voltage. So the y-axis represents the voltage. So, and same for the other one over here. So let's try and draw a sketch of both of them. The x-axis represents the time. So it's the time here, and voltage over here. Everyone happy with this? So just, they'll never give you the scale, the axes on there, but you should memorize that. For an oscilloscope, voltage is on the y-axis and time is on the x. Right, for a direct current, you know it's not going to change direction. It could look something like this. A straight line across. It will never drop below the axis. And for alternating current, it could look something like this. Makes sense? Why? It's constantly changing direction. That's why we're getting that nice squiggly line across here, similar to a transverse wave. Okay, so we've got direct current, alternating current. We've got two oscilloscope diagrams. We can see for direct current, the oscilloscope traces horizontal line, and for alternating current, the trace is a nice sinusoidal wave. Right, now let's scroll down. Test your understanding. What I didn't tell you is that the piece of graph paper has a scale on here, but it changes according to what you've set it as. So we'll start looking at a problem, then you can identify what's going on. The oscilloscope trace is set at 2 volts per division. So that means 2 volts per division. That means every single square is worth 2 volts. So volts, therefore it's on the y-axis, therefore this one is 2 volts. This is 0, it's the horizontal. This one is 4 volts. Therefore this one is 6 volts over here. And this one over here is going to be 8 volts. Why? Because I'm going up in twos. I know it's 2 volts per division. Division means each square. Right, so question number 1. Is this AC or DC? Actually, let's draw the whole axis on here. So I'll draw the voltage bit there. Actually, let's change colour pen for that. Let's change it to a blue. So voltage is there, and we're going time over here. So time over here. Right, so question number 1. Is this AC or DC? Well, you know it's a horizontal line, therefore this is going to be DC. 1 mark. Question 2. What is the peak voltage? So what is that voltage that we're seeing? What is that voltage? Well, you know each square is 2 volts. Therefore, 2 volts, 4 volts, it's going to be 6 volts. Can we see that? That line is on the 6 volt line. So that was 2, 4, that's 6 volts over here. Easy stuff. We can now move on. Right, so let's scroll down. Next question. The oscilloscope trace is set at 2 volts per division again. So it's 2 volts per division. Yeah, for every single square it's 2 volts. And 5 milliseconds per division. 5 milliseconds per division, that's for the time. So notice we've got 2 scales once again. So this is our X and Y. This is going to be voltage. This is going to be time. So question number 1, is this AC or DC? This is going to be AC. Why? Because we can see that the voltage is changing direction. So it's AC, easy stuff. What is the peak voltage now? Right, you know that's the horizontal axis. Oh, let's go back. So you know it's going to be 2 volts per division. So this one is 0 over here. This one is 2. This one is 4. So the peak of the wave is going to be over here. Therefore, it's 4 volts. Everyone happy with that? So this is going to be 4 volts. Why? It's the top part of that wave. Now, question 3. What is the time period? So you need to use your knowledge from the previous topic about waves. The time period is the time taken. So the time period, bit of recap, is going to be the time taken for one wave. So for one wave is the time taken. So what is that time? So let's look at, I'm just going to change the color of the highlighter. Let's go for, there we go. Let's go change it over here. So one wave is all the way up and all the way down. There we go. Right, how many squares is that going across horizontally? So we know that each square is 5 milliseconds. So we've got, this is 0. So this is 5 milliseconds over here. 5, so there's 4 squares. So 1, 2, so 1, 2, 3, 4 squares over here. Let's remove that. So we've got 4 squares, and each one of the squares is 5 milliseconds. So I've got 4 times by 5 milliseconds. That's the time taken for one wave. So milli, I must convert that into, get rid of the milli actually, so I need to divide by 1,000. So we have 4 times by 5 over 1,000. That will give me the time period. So we have 4 times by 5 over 1,000. I'm getting 0.02 seconds. 0.02 seconds. Everyone happy? Easy stuff. So once again, to work at the time period, I need the time taken for one complete wave. I know there are 4 squares, and I know each square is 5 milliseconds per division. Notice it's 2 volts for the y-axis, milliseconds for the x-axis. Right, so we've got the time period over here. What about the frequency then? So the frequency. So we've got the time period. Scroll down a bit. We also know that the frequency is equal to 1 divided by the time period. So frequency will be given by 1 divided by 0.02. So 1 divided by 0.02, I'm getting 50 Hertz. And that's that answer over there. So there we go. We've done this is a bit harder than before. Make sure that you look carefully at the oscilloscope trace. You look at the value of each division. It will tell you in the question though, so you're not going to be left to work out by yourself. Easy stuff. Now, summary. It's going to be the following. Direct current flows in one direction only. Alternating current constantly swaps direction. It goes one way and swaps and swaps and swaps again. An oscilloscope is used to view both AC and DC supplies, and the direct current graph looks like that, a horizontal line. The alternating current goes up and down like a transverse wave. And that's it for today's session. We shall see you next time for another cool lesson in Superphysics. Bye bye.